Welcome to this video on the physics of light, exploring everything from the rules of refraction to the visible magic of the rainbow. The three-step process: when sunlight enters a raindrop, it undergoes a transformation. Refraction, the entry. As light enters the water droplet, it slows down and bends. Because white light is made of different wavelengths, colors, each color bends at a slightly different angle. Violet bends the most, and red bends the least. Reflection, the bounce. The light hits the back of the droplet. Instead of passing through, it reflects off the inner surface like a mirror. Dispersion, the exit. As the light leaves the droplet, it bends again. This second bend fan out the colors even further, making them visible to the human eye. In this video, we are looking at why our eyes sometimes deceive us. Look at this pencil in the glass of water. From the side, it looks broken or bent at the surface. This isn't magic. It's a fundamental property of light called refraction. Definition: refraction is the change in the direction of light as it passes obliquely from one transparent medium, like air, into another, like water. Why does it bend? The mechanism. To understand the bent pencil, we have to look at two things: speed and medium density. The speed shift light is fast, but it's not always the same speed. It travels slower in optically denser mediums like water, and faster in rarer mediums like air. The bending rule: when light travels from water dense to air rare, it speeds up and bends away from the normal, the imaginary 90 degrees line. The brain's logic: our brains assume light travels in a straight line. When we look at the submerged pencil, our eyes trace the refracted rays straight back, creating a, quote, virtual image that appears higher and shifted from the actual position. In Class 10, we don't just observe the bend, we calculate it. There are two key pillars you need to remember for your boards. 1. Refractive index, N. This value represents the bending power of a medium. It is the ratio of the speed of light in a vacuum to the speed of light in that specific medium. N equals Vc. 2. Snell's law. This is the second law of refraction. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. N1 sine theta 1 equals N2 sine theta 2. Refraction isn't just for pencils and glasses. You see it everywhere. Apparent depth. Have you ever noticed a coin at the bottom of a bucket looks closer than it is? That's refraction lifting the object's image. The broken straw. Similar to our pencil, the change in medium creates a visual disconnect. Atmospheric refraction. Mirages. On hot highways, the air near the ground is hot and less dense. Light from the sky bends through these layers, creating an illusion of water on the road. To wrap up, remember, light bends because it changes speed. It bends towards the normal when entering a denser medium, and away from the normal when entering a rarer one. This simple bend is responsible for some of the most beautiful illusions in nature. We saw how a pencil bends in water. Today, we're looking at something even more precise: refraction through a rectangular glass slab. When light hits a glass slab, it doesn't just bend and stay bent. It goes through a double transformation that leads to a very cool geometric result. Imagine light as a runner, moving from a paved road into a sandy beach and back onto the road again. Let's track that journey. A glass slab has two parallel faces, which means light has to deal with two different boundaries. The entry, air to glass. As light enters the slab, it moves from a rarer medium to a denser medium. It loses speed and, like a car hitting a patch of mud, it tucks inward, bending towards the normal. The exit, glass to air. Now, as it leaves the other side, it moves from dense glass back into rare air. It regains its speed and kicks outward, bending away from the normal. Because the sides of the slab are perfectly parallel, it bends outward by the exact same amount it bent inward. Here is the magic of the geometry. Because the two bending actions cancel each other out, the emergent ray, the light coming out, is perfectly parallel to the incident ray, the light that went in. In your exams, remember this golden rule. The angle of incidence, I, is always equal to the angle of emergence, E. I equals E. Even though the rays are parallel, they aren't on the same track. If you draw a dotted line showing where the light would have gone if the glass wasn't there, you'll see the real ray has sidestepped or shifted. We call this perpendicular distance lateral displacement. Think of it like a train switching tracks. It's still going the same direction, just on a different line. What controls the shift? Not all shifts are equal. If you want to increase this sidestep distance, you have three knobs you can turn. Thickness, T. A thicker slab gives the light more time to travel at an angle, leading to a bigger shift. Angle of incidence, I. The more steeply you aim the light, the further it will jump. Refractive index, N. If the material is, quote, optically thicker, like a diamond slab, the bend is sharper and the shift is wider. To find the exact distance, D, we use this formula. D equals cos RT dot operator sine, I minus R, where R is the angle of refraction inside the glass. Light through a slab undergoes two refractions. It enters, bends, exits, and bends back. It ends up parallel to its original path but shifted to the side. Snell's law defines the relationship between the angles of incidence and refraction. The ratio of the sines of these angles is a constant, known as the refractive index of the second medium relative to the first. The absolute refractive index, N, is a measure of how much a medium slows down light. Higher N values, like in diamond, cause a drastic reduction in light's velocity. Class, we've seen that light bends, but now we're going to talk about how and why. Light is like a driver that changes its steering based on the road conditions. In physics, we call these road conditions the optical density of a medium. There are three specific scenarios light encounters. Let's break them down. Scenario 1. Entering the crowd, rarer to denser. Imagine light moving from the open air into a solid block of glass. Air is rarer, less crowded, and glass is denser, more crowded. The reaction. As light enters that crowded glass, it hits a speed bump. Its velocity drops. The direction. Because it slows down, it takes the path of least resistance and pulls closer to the normal. The math. In this case, the angle of incidence I is always larger than the angle of refraction R. Scenario 2. The great escape. Denser to rarer. Now, what if light is traveling through water and suddenly hits the air? It's going from a dense medium to a rare one. The reaction. It's like light just finished a difficult race and finally hits a clear track. Its velocity increases. The direction. As it speeds up, it swings wide, bending away from the normal. The math. Here, the angle of refraction R becomes larger than the angle of incidence I. Scenario 3. The straight-through rule. Normal incidence. There is one exception to the bending rule. If light hits the boundary exactly at 90 ring operator, meaning it is perfectly perpendicular, it doesn't bend at all. The catch. Even though the direction stays perfectly straight, the velocity still changes. The angles, both the angle of incidence I and refraction R, are zero-ring operator because they are measured from the normal. It goes straight through like an arrow. If you're wondering why a change in speed causes a change in direction, think of a marching band. Imagine a line of soldiers marching from a smooth paved road, rarer/fast, into a thick, muddy field, denser/slow, at an angle. The soldiers on the right hit the mud first. They slow down immediately. The soldiers on the left are still on the pavement, moving at full speed. Because one side is moving faster than the other for a split second, the entire line pivots. That pivot is exactly what light does. It's not just a change in speed, it's a change in the front of the light wave that forces it to turn. To keep it simple for your exams, slower medium equals bends towards normal. Faster medium equals bends away from normal. Head on, 90 ring operator equals no bend, just a speed change. We've all seen it. You're driving down a highway on a blistering hot afternoon, and way up ahead, the road looks soaking wet. You see a shimmering pool of water reflecting the sky, but as you get closer, it vanishes. This is a mirage. It's not a hallucination. It's a real physical phenomenon caused by a temperature battle happening just inches above the ground. On a hot day, the sun doesn't just heat the air, it bakes the asphalt. This creates a sandwich of air layers with different densities. Near the ground, the air is scorching hot. Hot air expands, making it less dense, rarer. Higher up, the air is relatively cooler and more dense, denser. Think of it as a slide made of air. The further down you go, the faster light can travel. Now, let's trace a ray of light coming from the blue sky down toward the road. As the light moves from the cool, dense air into the hotter, rarer air, what does it do? It obeys the rule we learned. It bends away from the normal. As it hits layer after layer of even hotter air, it keeps bending further and further away until it's moving almost horizontally. Eventually, the angle becomes so shallow that the light performs a U-turn, a process called total internal reflection, and starts curving back up toward your eyes. Here is where your biology clashes with physics. Your eye receives these light rays coming from below your eye level. They are literally coming up from the ground. The physics: the light took a curved U-shaped path. The perception: your brain is a straight-line processor. It cannot imagine light curving. It traces those rays back in a perfectly straight line, projecting them deep into the ground. This creates a virtual image. Your brain thinks it is seeing an object located under the asphalt. So if there's no water, why does it look like a lake? What you are actually seeing on the ground is a virtual image of the blue sky. Because the hot air is constantly rising and moving, convection currents, the image shimmers and ripples. To our brains, shimmering blue on a flat surface equals water. In the desert, travelers see a lake that is actually just the sky being reflected off the hot sand by the power of refraction. To summarize for your exams: cause, temperature gradient, hot air below, cool air above. Action: light bends away from the normal as it moves into hotter, rarer air. Result: light curves up. The brain projects a straight line downward. 4. Observation: a virtual image of the sky appears on the ground, mimicking water. Nature isn't lying to you. Your brain is just trying to make sense of light that took the scenic route. Class, did you know that when you look up at the night sky, you aren't seeing things exactly where they are? In fact, you've been looking at a slightly edited version of the universe your whole life. Because our atmosphere isn't a vacuum, it acts like a giant, moving lens. This creates two major effects: the shift and the twinkle. First, let's talk about position. Space is a vacuum, the ultimate rare medium. Our atmosphere gets progressively denser as you move toward the Earth's surface. The physics: as starlight enters the atmosphere, it moves from a rarer medium to a denser one. It doesn't just bend once, it bends continuously towards the normal. The illusion: this bending curves the light downward toward your eyes. But, as we know, our brains trace light back in a perfectly straight line. The result: this makes the star appear higher in the sky than its actual position. The early sunrise fact: this same shift gives us extra daylight. Because the atmosphere bends sunlight around the curve of the Earth, we see the sun about 2 minutes before it actually crosses the horizon in the morning, and 2 minutes after it has physically set in the evening. That's 4 minutes of bonus sun every day, thanks to refraction. Now, why do stars flicker or twinkle? This is officially called atmospheric scintillation. The cause: the atmosphere isn't a static block of air. It's a turbulent soup of moving layers, changing temperatures, and shifting densities. The process: think of a narrow beam of starlight. As it passes through these moving layers, it gets refracted zigzaggedly in different directions. The result: to your eye, the star appears to shift position rapidly and change in brightness as the light is momentarily focused or defocused. That dancing light is what we call a twinkle. This is a favorite question for board exams. If stars twinkle, why does Jupiter or Venus look like a steady, solid glow? It comes down to size and distance. Stars are point sources. They are so far away, they act like a single, tiny dot of light. A single pocket of moving air can easily knock that one beam off course. Planets are extended sources. Because they are closer, they appear as tiny disks, even if they look like dots to the naked eye. They send multiple beams of light toward us. The cancellation effect: while one beam from the planet might be bending left, another beam from the other side of the disk is bending right. These fluctuations average out and cancel each other, resulting in a steady, constant light. So keep these points ready for your notes. Atmospheric refraction: bends light toward the normal, makes stars look higher. Advanced sunrise/delayed sunset, caused by the same bending at the horizon. Twinkling, caused by moving air layers refracting point source starlight, planets. Don't twinkle because they are extended sources that average out the flickering. Next time you're stargazing, remember, you're looking through a beautiful moving filter that's shifting the whole universe just a little bit. Class, what if I told you that every single day of your life is actually 4 minutes longer than it should be? It's not a glitch in the Earth's rotation. It's a celestial sleight of hand caused by our atmosphere. Because the Earth is wrapped in layers of air, it acts like a giant curved lens that can actually bend light around the corner of the planet. Today, we're looking at the horizon illusion. Imagine the sun is still hidden below the horizon. Technically, it's dark, but the sun's rays are hitting the top of our atmosphere at a very shallow angle. The physics: as sunlight moves from the vacuum of space, rarer, into our atmosphere, denser, it slows down and bends towards the normal. The curve: because our atmosphere is curved like a ball, that light follows a downward path, hugging the Earth's curvature. The result: when that light hits your eyes, your brain traces it back in a straight line. This lifts the image of the sun by about 0.5 ring operator, just enough to make it appear above the horizon when it's actually still below it. This lifting effect has a direct impact on our clocks. We call these the 2 bonus periods, advanced sunrise. We see the sun about 2 minutes before it actually reaches the horizon in the morning. Delayed sunset. We continue to see the sun for about 2 minutes after it has physically dipped below the horizon in the evening. That's 4 extra minutes of sunlight every single day. If Earth had no atmosphere, like the moon, the sun would simply pop into view and snap out of existence instantly. Have you ever noticed that a setting sun doesn't look like a perfect circle? It looks a bit squashed or oval-shaped, like someone is pressing down on it. This is a brilliant example of differential refraction. The bottom edge of the sun is closer to the horizon, meaning its light passes through slightly denser air than the top edge. Because the air at the bottom is denser, it refracts or lifts the bottom of the sun more than the top. This vertical compression makes the sun look like a flattened disk right before it disappears. If you get a question on why the sun is visible before sunrise, here are your keywords: medium change, vacuum to atmosphere, rarer to denser. Action. Light bends towards the normal. Apparent position: the sun is optically lifted by 0.5 ring operator. Duration: 2 minutes early in the morning, 2 minutes late in the evening. So, the next time you're watching a beautiful sunset, remember, by the time you see the sun touch the horizon, it's already gone. You're just looking at its ghost image. Quick discussion question. If the Earth's atmosphere suddenly became twice as thick, do you think the day would become longer or shorter? Why? Hint. Think about how much more the light would bend. We've spent the last few lessons talking about light bending as a single unit. But now we're going to peel back the curtain. White light isn't actually white. It's a crowded bus full of 7 different passengers. When that bus hits a glass prism, those passengers don't stay together. They split up. This beautiful separation is called dispersion. Why do they split? It comes down to a simple rule. Different colors have different speeds in a medium. In the vacuum of space, every color travels at the exact same speed, about 300,000 kilometers per second. But the moment they enter glass or water, the medium becomes discerning. Violet and blue, high frequency. These are short, energetic waves. They interact strongly with the atoms in the glass, which slows them down significantly. Think of them as runners trying to sprint through high grass. Red, low frequency. These are long, lazy waves. They glide through the atoms with very little interference, maintaining a higher speed than the others. They are like a heavy truck that just keeps rolling. Because the speed v changes differently for each color, the refractive index n is actually different for every wavelength. Remember our formula, n equals vc. Since violet is the slowest versus is small, its refractive index is the highest. Since red is the fastest, its refractive index is the lowest. Mathematically, n violet greater than nred. Now, let's apply Snell's law. If the refractive index is higher, the bend is sharper. When white light hits the prism, violet has the slowest speed and highest refractive index. Result? It bends the most. Red has the fastest speed and lowest refractive index. Result? It bends the least. This creates the famous VIB-Gior spectrum. Red is always at the top of the fan, and violet is always at the bottom. The prism doesn't create these colors. It simply reveals them by giving them different exit ramps. Nature does this on a massive scale every time it rains while the sun is shining. Every single raindrop acts like a tiny liquid prism. Entry. Light enters the drop, refracts and disperses. Splits. Internal reflection. The colors hit the back of the raindrop and bounce back. Exit. The colors exit the drop, refracting again and spreading even wider before hitting your eyes. You are seeing millions of tiny prisms working together to paint the sky. To wrap up, here are your board exam bullet points. Dispersion, the splitting of white light into its constituent colors. Cause, different colors travel at different speeds in a medium. The winner, red travels fastest and bends the least. The loser, violet travels slowest and bends the most. VIB-Gior, the order of the spectrum from the base of the prism upwards. The critical angle sequence shows that as the angle of incidence increases, light can transition from partial reflection to total internal reflection. This happens when the angle of refraction reaches 90 degrees. We've all seen a rainbow stretching across the sky after a storm. It looks like a giant, painted arch, but it's actually a massive physics experiment. Every single raindrop in the sky is acting like a tiny spherical prism. For you to see those colors, light has to go through a very specific 3-step obstacle course inside every drop. If even one step fails, the rainbow disappears. Let's follow the light. The journey begins when sunlight hits the front surface of a raindrop. It's moving from the thin air, rarer, into the thick water, denser. The physics. The light slows down and bends towards the normal. The result. This is where the magic starts. Because white light is a mix of colors, and each color has a different frequency, they slow down by different amounts. Dispersion begins right at the front door. The white light starts splitting into the Vibgyor spectrum immediately. Now the light is traveling through the water and hits the back of the droplet. You might think it would just pass through and come out the other side, but it doesn't. The physics. Water has a critical angle of about 48 ring operator. If the light hits the back surface at an angle greater than this, it can't escape. Instead, it performs total internal reflection. The result. The light bounces off the back wall of the drop like a mirror, staying inside the water and keeping those newly separated colors organized and heading back toward you. Finally, the light reaches the front of the drop again and prepares to leave. It's moving from water, denser, back into the air, rarer. The physics. The light speeds up and bends away from the normal. The result. This second bend is the amplifier. It fans the colors out even wider. Without this final exit bend, the colors would be too close together for your eyes to distinguish the red from the violet from kilometers away. To understand how precise this is, imagine if we changed the rules. No dispersion? You'd see a white bow or a bright fog. No colors. No reflection? The light would go straight through the rain and away from you. You'd have to look directly at the sun to see anything, which we know is a bad idea. No final refraction? The colors wouldn't spread enough. They would just look like a blurry, pale smudge. Here is the final board exam secret. Why is red always on the outside of the arch and violet on the inside? It's all about the exit angle. Because of their different speeds, red light always exits the drop at an angle of 42.4 ring operator. Violet light always exits at a sharper angle of 40.7 ring operator. Because red comes out at a higher angle relative to your eye, it appears higher in the sky. This constant geometry is why every primary rainbow in human history has had the exact same color order. When writing your long answer questions, remember the big three events: refraction and dispersion at the entry, total internal reflection at the back, refraction again at the exit. Next time it rains, look at the sky and remember, you're looking at millions of tiny spheres performing perfect geometry just for you. If a rainbow requires total internal reflection, why don't we see rainbows at night with moonlight? Or do we? Search for moonbows.